Finally, let's examine how the distribution of iron in the body is controlled. Recall that iron enters the body via enterocytes in the duodenum, which is only 10 to 15% absorbed. Daily iron intakes are 1 to 2 milligrams. Blood contains about 3 milligrams of iron in transferin. Iron is contained in every cell as a part of the enzymes. About half a gram is included in myoglobin. The leading mobilizable stores, about 1 gram, are in hepatic ferritin, but the most significant iron content of 2.5 grams is in erythrocytes and in the reticuloendothelial system, where there is also, through erythropoiesis, the most considerable iron turnover, 24 milligrams per day, which can be further increased when erythropoiesis is increased. Iron content is controlled locally at the cellular level and the overall organism level. Local regulation of cellular levels is provided at the translation level. When iron levels decrease, the production of transferrin receptors and DMT1 transporters increases, increasing iron influx into the cell. At the same time, the decrease in ferroportin translation will reduce iron efflux from the cell, and subsequently the iron level in the cell will begin to increase. A higher level of iron in the cell has the opposite effect. A decrease in the production of transferrin receptors and DMT1 transporters will reduce the influx of iron into the cell. An increase in ferroportin production will increase iron efflux from the cell and not allow further increases in iron levels. In addition, an increase in apoferritin formation will allow more iron to be stored in ferritin and prevents the rise of the free iron pool, which can cause cell damage. The body must ensure enough iron in the cells and prevent excessive iron accumulation. Iron distribution is controlled by hepcidin at the organism's level. Hepcidin influences the release of iron from the cell via ferroportin receptors. An increase in hepcidin decreases cellular iron uptake, while a decrease in hepcidin increases iron uptake. In our diagram, we show this by narrowing or widening the ferroportin icons. Hepcidin reduces the concentration of ferroportin receptors. It binds to ferroportin, which is internalized into the cell and degraded in lysosomes. The function of hepcidin is to affect the absorption and redistribution of iron in the body. Increased hepcidin levels decrease the concentration of body available iron in plasma and, conversely, increased dipole iron in cells, especially in enterocytes, hepatocytes, and the monocytes macrophage system. Increasing hepcidin levels during inflammation prevents iron efflux through ferroportin and hides iron in cells. Thus, it prevents microbes from accessing iron and using it as a growth factor. The role of hepcidin in regulation iron uptake from duodenal enterocytes is critical. Hepcidin ensures increased iron uptake into the body during iron deficiency. However, hepcidin also prevents iron overload in the body, and increased hepcidin reduces iron absorption. Since the body has no regulation of iron output from the body, the only way to prevent iron overload is to reduce iron absorption through regulation via hepcidin. On the other hand, lowering hepcidin levels during increased erythropoiesis will ensure sufficient iron for erythroblasts in the bone marrow by increasing iron release from reticuloendothelial macrophages and mobilizing iron stores from hepatocytes. Now, play with the iron distribution model to better understand hepcidin's regulatory role and review the following problems.